In this example, we will solve a problem related to a thick-walled cylinder subjected to internal pressure. The objective is to determine the maximum hoop stress, the minimum hoop stress, and to understand how stress is distributed across the thickness of the cylinder. We are given a thick cylindrical shell with an inner radius of 10 centimeters and an outer radius of 16 centimeters. The cylinder is subjected to an internal pressure of 70 megapascals, while the external pressure is 0. First, let us confirm that this is a thick cylinder. The thickness of the cylinder is the outer radius minus the inner radius, which is 60 millimeters. When we compare this thickness to the inner radius, the ratio is much greater than 1. Therefore, this cylinder must be analyzed as a thick-walled cylinder, and Lame's theory is required. Next, we sketch the problem. We draw a hollow cylinder and label the inner radius as 100 millimeters and the outer radius as 160 millimeters. The internal pressure acts on the inner surface, and there is no pressure on the outer surface. Sketching helps us visualize where the maximum stress is likely to occur, which is usually at the inner surface. Now, we list the known values. The inner radius is 100 millimeters. The outer radius is 160 millimeters. The internal pressure is 70 mm, and the external pressure is 0. The next step is to define the boundary conditions. In thick cylinder analysis, boundary conditions are based on radial stress. At the inner surface, the radial stress is equal to the internal pressure and is compressive, so it is taken as minus 70 m. At the outer surface, the radial stress is equal to the external pressure, which is 0. Now we apply Lame's equations. According to Lame's theory, radial stress is equal to a constant A minus another constant B, divided by the radius squared. Hoop stress is equal to the same constant A plus B, divided by the radius squared. The constants A and B are determined using the boundary conditions, by substituting the boundary conditions into the equations and solving them simultaneously. We obtain the values of the constants. The value of A is approximately 44.87 megapascals, and the value of B is approximately 1.149 megapascals meter squared. Next, we substitute these constants back into Lame's equations. This gives us expressions for radial stress and hoop stress that are valid for any radius between the inner and outer surfaces of the cylinder. To find the maximum and minimum hoop stresses, we evaluate the hoop stress at the inner and outer radii. The maximum hoop stress occurs at the inner surface, where the radius is 100 millimeters. The value of the maximum hoop stress is approximately 159.7 megapascals. The minimum hoop stress occurs at the outer surface, where the radius is 160 millimeters. The value of the minimum hoop stress is approximately 89.7 megapascals. Now, let us discuss the stress distribution. Hoop stress decreases gradually from the inner surface to the outer surface of the cylinder. This means the material near the inner surface experiences the highest tensile stress. Radial stress, on the other hand, starts at minus 70 megapascals at the inner surface and increases steadily to 0 at the outer surface. Finally, we sketch the stress distribution graph. On the horizontal axis, we plot the radius, and on the vertical axis, we plot stress. The hoop stress curve slopes downward from the inner radius to the outer radius, while the radial stress curve slopes upward from negative pressure to 0. In conclusion, the maximum hoop stress in this thick cylinder occurs at the inner surface and is about 159.7 megapascals. The minimum hoop stress occurs at the outer surface and is about 89.7 megapascals. This example clearly shows that stress in thick-walled cylinders is non-uniform and must be analyzed using Lame's theory.